NENOMATICA, where mathematics meets YouTube excellence. In this example, we will prove a clean fact about fractional parts. If x and y are real numbers, but not integers, and their sum is an integer, then the sum of their fractional parts is 1. Here is the statement we will prove, and then we will go through the proof in 4 clear steps. Step 1. Define the fractional part. The fractional part of a real number is the number minus its floor. We write the definitions for x and y. Quick challenge. If x equals 2.3, what is its fractional part? Step 2. Add the fractional parts. We add the two identities we just wrote, then algebraically regroup to get a very useful single expression. Step 3. Apply the given conditions. We are told that x plus y is an integer. Call it k. The floors are also integers. Call their sum m. Substitute to see the sum of the fractional parts equals k minus m, which is an integer. Pause and notice what must be true about the exact value of that integer once we think about ranges. Step 4. Use the range of fractional parts. A fractional part is strictly between 0 and 1 for a non-integer. Adding those ranges, the sum is between 0 and 2. Since the sum is also an integer from the last step, the only possibility is 1. Let's reinforce with 2 quick examples. Example: for 1.2 and 2.8, the fractional parts are 0.2 and 0.8, which sum to 1. For negative 0.1 and 1.1, the fractional parts are 0.9 and 0.1, 0.9 and 0.1, which also sum to 1. We will solve a fractional part and floor function example following the exact 3-step algorithm shown, and we will highlight every change clearly as we go along. First, we display the example and the problem statement. Step 1. Identify the fractional parts. We recall the definition. Then we compute the fractional parts of x and y. The fractional part of x equals 0.73, and the fractional part of y equals 0.27. Quick challenge. If x equals 5.1, what is its fractional part? Step 2. Calculate the sum of the numbers. We use a simple addition property. Then we compute x plus y. 3.73 plus 2.27 equals 6, which is an integer. Notice how two non-integers can sum to a perfect integer. Step 3. Calculate the sum of the fractional parts. We use the sum of fractional parts notation. Then we add the fractional components. 0.73 plus 0.27 equals 1. Since the total x plus y is an integer, and neither x nor y is an integer, the fractional parts add to 1. We now present the final result exactly in the structure of the input solution. In this lesson, we will prove a useful theorem about the floor function, sometimes called the bracket function. We will also check a concrete example first, and then present a clean, rigorous proof. First, let's see an example and verify the statement numerically before proving it. Step 1. Use the definition of the floor function to evaluate the brackets. The floor of a real number is the greatest integer, less than or equal to that number. Step 2. Use distance as the absolute difference and compare to 1. Now that the example checks out, let us prove the theorem for all real numbers. We will follow a clear 4-step structure. Step 3. Assume the floors are equal to the same integer, n. Step 4. Apply the floor definition to both x and y. This places x and y inside the same unit interval from n to n plus 1. Step 5. Subtract the inequalities to create upper and lower bounds for x minus y. Step 6. Convert the two-sided bound into an absolute value statement. If a number lies strictly between negative a and a, then its absolute value is less than a. Summary. We use the floor definition to put x and y in the same unit interval, subtracting inequalities bounded x minus y strictly between negative 1 and 1, and we concluded the absolute difference is less than 1. Quick challenge. Try x equals 3.2 and we concluded the absolute difference is less than 1. We will prove a classic floor function identity using the exact step order shown. Start, zero sum, group simplify, and integer property. Below the example label, we display the statement in bold orange. Step 1. Start with the original expression. Quick challenge. Do you know the zero-sum trick? We use the additive identity idea. Adding and subtracting the same quantity is adding 0. then apply it inside the floor. Now group and simplify. Combine the two negative halves to get -1, and pair the positive half with x. A key floor function rule says shifting by an integer k can move outside the brackets. We apply it with k equals -1. Conclusion: we have shown the identity holds exactly as stated. Let us summarize the key ideas. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.